Ladies and gentlemen, thank you so much for being a part of this session. Today's session, this session is very special. This is a track 6, and it has been a privilege for us to actively have 2-day session starting yesterday with the presence of Dr. Girish Gyani, sir, who is the Director General for Association of Healthcare Providers of India. Also, I did have a privilege to also have Dr. Naveen Thakkar, who is also the Honorary Secretary for Indian Orthopaedic Association. So yesterday's day, ladies and gentlemen, it was very detailed in terms of covering various aspects in terms of medical devices, even in 3D printing and 3D visualization. In terms of AR and VR was also part of the discussion, because 3D graphy, holistically, we are covering all the 3D technologies and how medical practitioners from various different specialization, may it be orthotics and prosthetics, which was the second track. We also discussed on tissues, hard and soft tissues. Very, very interestingly, even in the morning, we had one session on dental applications, where we had the Association of Oral Maxillofacial Surgeons of India and Indian Society of join to also understand how this technology can be used in various aspects. Even simulation software was actually being discussed, because that kind of an interaction was very limited and very less comparatively. So I welcome you all for this wonderful session, and it's a privilege to be also associated with the Indian Orthopaedic Association. Also, Dr. Naveen Thakkar also is there, the Honorary Secretary for Indian Orthopaedic Association. I also have the privilege to also have Dr. Atul Srivastava. Sir, very good afternoon. He's the President-elect, and I look forward to his engaging participation, because this is a technology which is not the future, it's already the present, because a lot of traction is already happening with dental and medical. But orthopedics, I'm sure, as we progress and get to know about this technology in detail, we'll get to know where all this can be really implemented and how best we can make the best solution, provide the end user, the patients. And also trying to see how patient satisfactory index, gentlemen, can be really kept in the right course in terms of for us to attain that. So now also Dr. Vikas Jain, the past president of Gujarat Orthopaedic Association. Sir, thank you so much for your support. You are more like a technology respondent in your blood. So that was a very good, timely, engagement for us to connect with each other. Also understand where the gap is. So doctor comes with various knowledge in terms of his specialization in orthopedics, and served in the area for many years. So it's a privilege, doctor, to be part of the 3D Graphy Consortium. He's also the advisory and also being a key respondent for 3D Graphy. And then to not miss out some of the respondents who've taken the mettle in terms of offering solutions in orthopedic surgery with orthopedic implants. Mr. Sushantji, he's also a patron, always a support, because he understands the importance of new technology. Also somebody who has actually been the help also to manufacture modular implants for the last 35 years, ladies and gentlemen, and also have a beautiful set up in Valsad. I did have an opportunity to visit that center, and also have introduced 3D technology companies to also come and understand what are the ways that we can actually see that we can serve and ensure that the gap can be filled for customized manufacturing going forward, with his interest. So thank you so much, sir, for your time, Sushantji, and good afternoon, and thanks for joining. And now then, I would like to introduce Mr. Jagannath, who is the technologist, who comes with his expertise in technology in 3D printing, a leading company by the name BFW. Ladies and gentlemen, they've been actually in CNC and machining and tooling for many years, for almost last 60 years. And now they also understand the potential of additive. So they have also engaged, and they've also partnered with and powered by Meltio. They've actually created a beautiful machine and technology, which is a hybrid machine, which has both CNC as well as 3D printing, the DD technology, which I'm sure Mr. Jagannathji will actually share, and we will also be able to gain some good information on that particular technology. I have Mr. Sudhakar also joined from EOS. They are also going to talk about how oyster integration with various with the technology that is here to offer in orthopedics can be a great game changer when it comes to oyster integration. So thank you so much, Sudhakar, for your time and your presence. And also Mr. Rajesh, who's also been an active respondent with us and who's been a part of our consortium, 3D Graphy. All of them are a part of the 3D Graphic consortium. And Rajesh has also been actively leading from the front from the organization called Monotech Systems. Now they are actually a buffet of technologies in terms of the offering. So they have partnered with various different companies in India, and primarily they come with an expertise in printing technology, inkjet printing, and now they also have 3D printing as one area of specialization. So it's really good to have all of your presence, and I'm sure it will lead and it could definitely help orthopedic surgeons who have actually many of them are also looking forward to learning how this technology can be really of good use. Thank you so much, sir, and thank you, Dr. Vikasji. I would now want you to lead the chair as a session chair and also moderate the session subsequently as we progress. Thank you so much.
Thank you, Dr. Shibu, for that beautiful introduction of the entire panel and as well as describing the functions of 3D graphy and creating this lovely ecosystem. So presently, we are focusing totally on orthopedics. And at one end of the spectrum, we have manufacturers who manufacture machines who could do a 3D printing. At the other end, we have few orthopedic surgeons represented well by Dr. Atul Srivastava, who is the President-elect of Indian Orthopaedic Association. We have Dr. Naveen Thakkar, who is Secretary General of Indian Orthopaedic Association. We have few orthopedic surgeons who have also joined as delegates. And unfortunately, we could not have Dr. Ramesh Sen, who is the President of Indian Orthopaedic Association, who is traveling to Kathmandu while we are having this program. And we also have, in a B2B segment, we have medical device manufacturing representation done by Orthotech and Mr. Sushant Banerjee, who's there. So now we have almost something in an entire spectrum. Yesterday, as I would only just give a short introduction to what was new, we were, for my fellow in orthopedic surgeons friends, we had a very good session coming from one of the key players from Chile. He has introduced an antimicrobial property which could be again used in 3D printing, which is very important for us as an orthopedic surgeons. There are few who came up with simulations. These simulations would help us to do all pre-operative planning, and then we can come up with patient-specific implants based on those simulations. And there were few who came up with softwares, and these softwares are very important for us, again for a pre-operative planning, and then to decide which particular implant would be best for one patient-specific fractures or patient-specific joint and bone disorders. So with this in mind, I think we'll start our program with the machine manufacturers, and I think we have Mr. Jagannath, who's first on the panel, who can start with his presentation.
Thank you. So I'll just share my screen, and for want of bandwidth, I'll just close this thing. You're able to see the screen?
Yes.
And am I audible clearly?
Yes, very clear.
So good afternoon to all of you, and I'm a little nervous because of a lot of surgeons sitting in the presentation, which is my first presentation with the surgeons who are specialists. But anyway, I'll try to do my best, and thanks 3D Graphy for giving me an opportunity and our company to present this, to talk about the product platform which we just launched this month. So we want to revolutionize manufacturing with Smart Factory and enhance your 3Ps: productivity, performance, and the precious time, which is most important in the medical segment. So BFW is one of the pioneers in the industry where M2 Next is a subsidiary. So this is a 6-decade-old company where we are manufacturing machine tools for the last 6 decades. We started our subject with the German engineering technology as a JV, Fritz Warner, and we have done a lot of localization here. We have full presence in aerospace, auto, diamond mold, railways, so on and so forth, and including medical and general engineering. We offer various CNC machines, to varied range of 450 models. So at one point of time, we wanted to start offering factory automation products. That is how, M2 Next was born, which is Industry 4.0, where we have typically four verticals. The first vertical is additive manufacturing on laser-based DED. We also have digital transformation, where we can acquire data and do analytics on every equipment what is being produced and which is running on any of the shop floor. We also do a lot of automation in terms of how to automate when an equipment runs on the shop floor. We use robot, cobot, so on. We also do process engineering, which brings in better efficiency in terms of how do we get the best out of the equipment at the end of the day. So we are primarily brand agnostic and offer complete turnkey solutions in manufacturing. So that is how the entire journey is going to be of M2 Next. Now, here on the portfolio, I would just like to emphasize two areas. One is the AGV automation, which can be a good solution for the medical requirement. We're already working on pharmacy. We are working on clean room applications. So on the medical domain, we can also look at AGV, and particularly on additive, we have hybrid and 3D printing solutions. In hybrid, you could build the part and to the required contour and finish the part without removing the part from the machine, which means that you can achieve micron level finish, surface finish of the part up and along with the contour. And this has a 5-axis capability, where there are 3 linear axis and 2 rotary axis, which I'm going to show you a little later. And along with that, if there are some very crucial contours, we can use a robotic additive. We can also use a gantry additive, where the voluminous part, which can be as big as 2 meter by 2.6 meter, can be built on gantry. So this is the brief portfolio. Now, what is the significance of additive in terms of medical domain? What is that we can offer? First thing is, this is a made in India product which we have launched. We look at how it can be made affordable in the country, particularly in medical domain, and which is used for creation of customized patient-specific prosthetics, insert and anatomical models, health restorative items and hardware. And we are also looking at quick turnaround time from scan to real implant, which means that I should be able to evolve a part, implant, finish the implant. Particularly if we take an example of titanium, say on an implant, I should be able to build and try to finish that, giving very little scope or opportunity for the surgeon to do any modification of the implant, wherein it should be able to fit in directly into the patient based on patient specific scan what is being evolved. So we are looking at true signs of disruptions here within the healthcare industry, and major innovation we want to be part of this, where we could create customized near net shape medical implants, which means that since we are part of every technology, be it pre-process, post-process, including creating a post-process using a CAM model, we can take this scan, convert it into an STL file, and then see how do we build the part and machine the part, and see what kind of oxidation levels can be achieved on titanium. If required, we can get into an argon chamber and build the part so that it is less than 50 parts per million kind of an impurity, which could be really beneficial in terms of the quality of the implant which goes into the patient. So I just want to dwell along direct energy deposition technology which is used here to make the. There are plenty of technologies in additive. One particular technology is direct energy deposition. We use a high power laser which is used to melt metal powder or wire supplied to the focus of the laser beam. The laser beam typically travels to the center of deposition head and is focused to a small spot by one or more lenses. The build occurs on a XY table which is driven by a toolpath created from a digital model to fabricate an object layer by layer, along with build monitoring through scanners. So this is what we typically do on a powder-based DED. On a metal wire-based DED, we feed wire through a nozzle instead of powder, which is again melted by a laser using inert gas, which could be an argon, in either an open environment or a sealed chamber, depending upon the impurity levels which is acceptable in the part when it is being built and machined. So typical solution would be a 6-axis articulated robot, 3 or 4-axis gantry, or a 5-axis machine. So where DED is used is coatings, repair, hybrid manufacturing, so on and so forth. So we can bring with both the chambers, open chamber and closed chamber, which we can supply along with the equipment, depending upon the quality of the part which needs to be achieved after we build and machine. So it can be an open atmosphere or a closed atmosphere, and with a shroud gas which could be good enough to build the part. Now let us look at the platform which is called a Photon H series, which we have launched, which is up and running in our technology center here in Bangalore at BFW. So this comes with an additive and a subtractive capability. As you can see on your right, when you are building the part where the head has really come down and the part starts getting built on the table. Now, once this part gets completed, you can see the subtractive spindle next to the part with a center distance, which is automatically the offset is taken by the machine, and the CNC will take over the machining, of the part, which means that you build the part and you complete the part with the machining on the same table. So here the entire system, if you see, you have the CNC controller on the right and you have the additive control on the left. And the building and machining is seamless, which means that we use a post processor, we use a CAM model, we get the STL file, we build the part, and with suitable offsets of the tool, automatically the tool changer selects the tool and then machines the part. So just to get a better view of the product, I will run a video which gives you an explosive view to show how the machine looks like. So this is how the complete machine, which is good to go on any shop floor, any laboratory, which is an industrial level machine, which has a laser safety glass in the front. And you can see the VMC with 5 axis, with 2 rotary tables and 3 linear axis. And depending upon the contour and the volume, you could build the part by programming on a post processor. So this is the laser head which comes down once it is wanting to do an additive process, and then goes back, and the same table moves towards the mechanical spindle, which can machine the component and finish the component. So on the right you see the CNC controller, and on the left you see the additive controller. So here, you could build the part based on any contour which is required, and you can finish the part and take it out, and we can go to any platform depending upon what kind of the requirement is there. So the 1000 platform gives you something like a 400 by 300 by 300 kind of a volume, which is good enough for the medical implants. Now the second platform what we have built is the robotic platform, which also has 6-axis articulated on the articulated robot with an extended positioner of 7th and 8th axis. So a total 8-axis combination could give you a 360-degree contour on the component, which is extremely difficult to build on a linear axis and a rotary axis. So this gives a full flexibility in terms of building. Only thing is, if you want to machine the part, you will have to remove this and take it out onto a CNC machine. But then the kind of typical contours which are limitation on a hybrid machine can be built on a robot, and the volume space what is available to run a CAM model based on the near net shape requirement, the robotic series, which is Photon R series, can be applied. Now, various parts which can be printed using the application, I will not get into the details of this, but typically the jaw implant, the surgical guides, the femoral stem, the skull cranial, hip cups, leg prosthetics, so on, can be achieved using this particular platform which I just showed you. Primarily, it is customization and personalization with superior finish. So this is something which, on a single setup, getting without the intervention of anybody after you build the part is the advantage. Optimal cost efficiency, because we are building the machine here with the complete post process, including the CAM model software. Enhanced productivity with versatile finishing capability, democratization and collaboration, wide variety of materials. You can go in for a combination of wire and powder to enhance adaptation of DED technology, which means that typically the wire is chosen when you want to have a very fast build rate. Imagine you want to build a part within 1 hour or 2 hours, the wire would be the right thing to do. And when you want to do a fine contour of the part, powder would be used. So the combination of both will give you accuracy as well as the speed in terms of the platform. And the hybrid would enable you to go and finish the part and be ready with respect to the implant, which would be the required thing for the patient. So typical application of LDED in medical is, most commonly used are patient-specific orthopedic implants, patient-specific surgical guides, mini plates for free flap fixation, customized prosthetics, coating on top of implants to enhance application and life of patient. So we also have a coating capability where we can use a third nozzle on the machine itself, where instead of doing an additive, you can do a fine spray coating of the powder, which would bring in the longevity of the implant itself because of surface coating. So finally, future ahead is most advanced, 3D printing solution is anticipated for complex implants. In situ printing, in which implants are printed just before surgery, is anticipated for future trend, where a patient would require quick attention because of various, issues with the patient, where the surgery has to happen instantaneously, and with patient-specific implant can be printed at site. This will advance to use for in situ repair of partially damaged, diseased, and fractured bones. This also the possibility what we are looking at. So finally, I want to conclude that LDED additive solutions can realize the implants to the finest contour with versatile metal range, starting from stainless steel to titanium to chromium cobalt to vanadium, so on and so forth, to suit every need from scan to implant, so that the surgeon or the domain expert needs to do what he needs to do, while we try to support entirely from the local capability and see that how much we can come closer to the orthopedic requirement. So with this, I would like to close the session and thank you very much for your attention, and would be happy to answer any kind of questions.
Thank you so much, Mr. Jagannath. That was really a very elaborative presentation, especially coming from the manufacturing, predominantly using the metal.
Yeah.
So we'll take the questions at the end of the session. Probably our orthopedic surgeons and our medical device manufacturers would like to ask you a few questions.
Sure.
But we'll move to the next presentation coming from Mr. Rajesh, who has also a manufacturing this thing using the other metal, other products also, like polymers and plastics. So can we have a presentation coming from you, Mr. Rajesh? He's from Monotech. You can share.
Sure. Yes, sir. Good afternoon. I'll just share my screen.
Sure.
Thank you, and good afternoon, and thank you all, Dr. Shibu, for having me on this medical, technology, additive being part of the technology for orthopedics. And as Mr. Jagannath said, I'm also not from the medical background, and so I'm also a bit nervous about this. But having said this, we are from the additive manufacturing industry, and we are more confident about talking about more about additive manufacturing with respect to medical. And I have here compiled some technologies which are utilized in the orthopedic fields, and there are some which will be the future for the industry. Just to give you a background on the AM in medical field, and there are various areas where this technology can be utilized, and for the various findings what you can actually look at. When you talk about orthopedic and maxillofacial, it is cost and time savings. Transplants, it's more about personalization. It's for students who can, it's a cost savings for the pathology specimens. Surgery, it improves the time savings, improved medical outcome, etc. Implants, dental, pharmacy. So you can see that in orthopedics, it is more about accuracy, cost and time savings, personalization, fully automated and digitized manufacturing. And this is what we are talking about today, and more about the orthopedics, how it can help, how additive manufacturing can help in all this. You can see that we are only talking about few uh, areas like implants, which is mostly to do with metals. But there are also other technologies which can be used by the doctors in the medical field for the favor of the industry and for themselves. Some various basic applications in orthopedics which we can talk about is testing and planning, where we can speed up the process in developing of new devices, and also we can create some sort of models which can be used for the better surgeries. And also we can talk about the implants and devices, which has been the main discussion throughout the last 2 days. Talking about testing and planning, so this is very important, because before even the planning of the surgery, if it's a very critical surgery, today with the digitization available, with the type of the DICOM to print softwares available in the market, it's easy to digitize and also convert a patient specific medical data into digital 3 model, plan it properly, design it to the requirement of the patient, manufacture it. This is where the manufacturing using additive manufacturing is very, very important for customized solutions. And inspect. So you can put models through 3D systems, through the intensive quality control system, and deliver a final models, guides, or implants. So the various technologies used for testing and planning could be like right from the software. If you talk about the hardware and 3D printing, we talk about metals, but there are many non-metal products which are useful for basic planning. So which is the stereolithography technology, which can make you translucent and transparent models to highlight vital structures. We can talk about opaque models, which are very functional and also very easy to understand the concept of pre-surgical planning. We have also the multi-jet printing and the color jet printing, which can give you highly full color output for you to distinguish between the various parts of the body, and also to do a proper surgical planning with implants. And if we talk about the products for anatomical models, we are talking about the basic resin-based technologies, which are useful for such models. And the materials available are all basically biocompatible materials. And there is a whole lot of technology, like in terms of softwares, which is DICOM, 3D Sprint, and Geomagic Freeform, which are available today for the for developing such models. So for the implants and devices, there are various benefits of 3D printing at the point of care. Today, we are talking about a lot of service providers supporting the doctors, but there will be a time where many hospitals will have the point of care system where the parts will be developed and printed in house, so that it could be utilized for very critical and very important surgeries. So the point of care has the benefits of increased accuracy, reduced procedure time, improved patient communication, better inventory control, and lower cost. So we are talking about supply chain, and due to Corona, there has been a lot of problems in terms of getting the parts or deliveries. With point of care systems, it is going to be easy, and additive manufacturing is going to make this happen. The point of care systems. I would like to just take you upon few devices which are used in plastics and resin polymers. We have some experiences in such parts where it is being used for total shoulder anthroplasty, for craniomaxillofacial hybrid guides, for ankle PSIs, which are printed through resin-based technologies, through the 3 systems figure 4 technology, and also the SLS, so the selective laser systems sintering system, which uses polyamides. And polyamides PA12 is a biocompatible material, and it is being used for various such applications. And going forward, and also with the SLA technology, which is a stereolithography technology, we can see that there are a lot of devices which can be printed with very good accuracy and finish, which can be part of the initial surgical planning and surgeries as well. And then devices in metals, of course. When we talk about metals, it's very well known that titanium and stainless steel, etc., are being used for devices and shoulder implants, into body fusion cages with inserters, and various hip implants. So there are a lot of materials available today with the powder bed technology and also the DED technology, which are really revolutionizing the devices in the industry. And we talk about implants in metals, then there is a whole lot of possibilities with the 3D printing and the metal 3D printers. And this is basically something which we can do with a powder bed fusion, direct metal bed fusion technology, where you can do a lot of integrate details for osseointegration and for very, very minute parts. So for the implants and devices, when we talk about, we always talk about metals, but there are also some technologies which are utilizing ceramics and wax. So wax also is one of the important part of medical, which we do not see, where it is going to be very low cost for certain surgical devices to be manufactured. So we also have wax 3D printing, through which few components can be easily made out of the investment casting. You do not have to go for molds or tools, which means it's a toolless digital manufacturing using wax. And then we talk about ceramics, which is a recent addition to our portfolio, and it's very important to consider this because this is going to be the future in terms of devices and implants. Because today we are using more of titanium, but the future is going to be either zirconia or hydroxyapatite, which is going to be revolutionizing. And you can see this part on the left. It's basically a very, very small part, very minute part with a lot of details. And it is used to target, it's a probe to target cancer cells. And this has been used for a breast cancer surgery. And this has been manufactured using the XJet ceramic technology. And this is one of the most recent technologies which uses nanoparticles instead of the micron level particles. And this can provide you the minutest of parts for surgical surgery and surgery supports. And then we talk about implants in ceramics, which of course with zirconia and hydroxyapatite is being widely utilized today. Hydroxyapatite also is being now developed through DLP technology, which can provide you this for the future implants. And zirconia, of course, is being used right now for the dental, but it also will be getting into the orthopedics in the future. So with this, actually, I would like to show you some two videos, which are for the ceramic applications, which will be showing you how this future is going to be with the implant.
Trying to diagnose and deal with breast cancer. In the U.S. alone, 41,000 women will die this year of breast cancer, and 500,000 will die worldwide. This despite advances in 3D mammography and other technologies. In the U.S. alone, 1 in 8 women will be diagnosed with breast cancer in their lifetime. Back in 2002, Marble MedTech recognized the potential value of MRI for detecting and treating breast cancer. However, as we got into this, we realized that there was even more potential value. This idea of using MRI to detect early stage cancers that are the most dangerous varieties that need to be found and early and treated is groundbreaking. Realizing that MRI could be used to guide minimally invasive treatment procedures, all we needed to do was develop an MRI compatible tool. For example, a cryotherapy probe that could be used inside the bore of the scanner while we're doing imaging to guide it. Right? A real breakthrough came when we realized that the nanoparticle jetting technology from XJet could meet our requirements for the very fine intricate details that we needed to make this MRI compatible cryotherapy. The The XJet system offers freedom of design that allows us to produce this very complex cryotherapy part, as well as many other parts with very complex, unparalleled ease of use. It's very efficient, environmentally friendly. It produces final parts that don't need any post-processing. Cleaning process is very easy, very fast. It's used now for doing production parts that are ready to be used, not just prototype parts. So we use our image guidance system to guide our cryotherapy probe to the cancer target. We will then apply the cryoablation technique that will freeze the breast cancer tumor, and we're done. We leave the tumor there after it's been destroyed, and the immune system cleans the tumor up. Through this process, the immune system can actually generate antibodies that can prevent the cancer from coming back. This will transform breast cancer healthcare completely by eliminating the need for doing many biopsies, surgery, chemotherapy, and radiation treatment.
Our solution, combined with XJet's production technology, which will be the new paradigm, this will not only allow us to offer groundbreaking treatment to patients in large hospitals, but also to those that are in community-based smaller hospitals. Our goal and vision is one day for women to go for an annual MRI screening, and if something suspicious is found, to be able to treat it preemptively. And what enables this vision to work is the system from XJet, which allows us to produce the right probes that work in an MRI environment to treat these women and save lives. Despite millions of dollars being spent on research trying to diagnose and deal with breast cancer, in the U.S. alone, 41,000 women were.
Sorry, just a minute, please.
I think the video is repeating, sir. Yeah.
Yes, so I have to go back.
So,
Yeah.
yeah.
So, yes. This is another video which is very interesting. If I shall show it, because this is also with how ceramics are being used for surgery. And just a 2-minute video, I will run it through quickly.
Hi, my name is Scott Burke. I'm the CEO of Beza. DSMI has been in operation for almost 20-some years. Rolls-Royce, anybody who's making high-volume subtractive manufacturing.
Beza is focused on manufacturing small, complex metal parts.
This requires precise, accurate, and especially repeatable manufacturing process. We think XJet can offer that, and it can be beneficial to a multitude of industries that we serve today. This includes automotive industry, medical industry, tooling industry, as well as many other final use of customer industries. The main decision driver for us choosing the XJet technology is the science, the physics behind the technology itself.
We were really intrigued with the technology and sending some sample parts to XJet, and then when they actually came back, that was the eureka moment.
Beza prides itself on being a small, complex metal part. We chose the XJet solution because it really rounds out our portfolio for our customers. And XJet really complements the small, complex metal part aspect of our business.
About the parts, what we really like is the beauty resolution, the capability of doing a very complex geometry, small holes, very sharp corners, very refined surface finishes that you can basically make a part that's right off the printer, doesn't need any post-processing, and is ready to use, ready for the final use, ready to go in the field and be a valuable part of the customer.
Now and not only can you make it, now you can mass produce it.
With our system, you can do your product development on the exact same equipment that you're going to go into production with, and drastically reduces product development timelines and time to market.
We want to be
this company Azot is actually using the XZ technology for making parts for the Da Vinci robotic surgical instruments. And this technology is being utilized very widely in part of the world. This uses a nanoparticle jetting technology, and if you see, this is one of the future for the industry with very micro and small surgical parts, surgical devices using ceramic and metals. So I would like to just close with some few slides about us. We are basically a 23-year-old company, and we were established in 1999 with 400 employees. And today we have 15 plus locations with 10 own brands. And we are also into the development of 3D printers. Apart from our 2D printing capabilities, we have 27 alliance brands, out of which 9 are 3D printing technologies, all the leading technologies we have. And we have 2 manufacturing facilities in Chennai and 1 in Delhi. And we have the locations all over India to support our customers support. And our partnership in 3D printing is with all the the giants of the world with respect to technology, right from scanning to printing of various materials, including wax, polymers, metals, ceramics, and metals. So what we say is that we are not specialists in medical, but we have the technologies and at least the know-how to understand which technology can go for which application in the medical industry. And we are able to provide you with the customized solutions which can help the medical industry. And I would like to conclude by saying that we are helping the medical industry to to choose the technology with respect to what applications they are looking at, and whether they have to go for the print services or they have to buy the 3D printers. And so we give a complete consultation. And with 3D printing, we also work on the design flexibility and the economics of printing with respect to the applications. And that's the value drivers are we reduce the manufacturing costs using IAM and with faster time to market and improve manufacturing and supply chain. We have around 19 technologies in our facility in Chennai, and we have the complete set of technologies right from all the materials which we could use for the industry. And we are also catering to the industry as well as the medical industry. I would like to stop here. Thank you very much for giving me this opportunity, and I hope these technologies could be utilized by the medical industry. Thank you very much.
Yeah, thank you. Thank you, Mr. Rajesh. That was really a very elaborate presentation. There would be some questions that we would all like to put you in the end of the session when we have a panel discussion. To take this stage ahead, I would like to request Mr. Sudhakar Gingade. He is a head application engineer, EOS, from the Indian branch. He'll be talking on 3D printing applications for orthopedic implants with polymer and metal both. So over to you, Mr. Sudhakar.
Yeah.
Your screen is in. Yeah. Thank you so much. We can start.
Yeah. On the context of the bandwidth, I've just switched off my video so that it'll be easier. Thank you and good afternoon, everyone. Thanks for 3D Graphy for giving the opportunity. Today I'll be talking more on the EOS based medical on the orthopedic side, what we are up to, what we are. So just to give you a small intro on just a single slide, that we are in present from 98 and we have more number of machines installed on the industry based customers, like for example not on the desktop or on the entry level. We are on the industrial based 3D printers. So we have more than around 5,000 systems sold in across the globe, and we are present more in 67 countries. And we also wanted to give you something like it's like an end-to-end solution and not like just a machine sale. We are OEMs, but we did do our 30 years of experience to be shared with technology to the industry. So that's where we came up with something called as like teaching, learning, or for the the industry and for the academia. So that's where we are coming up with those activities coming now. So I'll just tell you why I'm talking about that. It's called an end-to-end solution in the later part of my slides. So I'm going to talk more about the DMLS technology, which is called the direct metal laser sintering process, or the laser certification process. It is a powder-based technology. EOS technology is basically only on powders. We don't do anything other than the powder-based. So how it works? So right from a powder, you get the parts printed, and then you get the final product. So here you have you get the powder from one side, and there's a bed in the center, and on the left hand side where you have a collector bin. So there's a recoater which moves onto your right and left. Once the recoater just layers the powder, puts the layer, then you have the laser coming up and solidifies, and then you can get the part. So I don't want to go too much deep into this, because I think from yesterday people have been talking more on this. So we are into like more on these areas that we have done. So I've personally been working with the medical field from 2015, very closely with the medical field. So prior to that, we were not so much involved or active on this industry, but now we have been actively involved in these areas. So we have a material. See, whenever you have a process, whenever you have in the medical field or in your in the aerospace areas, the major problems are the materials, are the what kind of materials that needs to be used, because it goes into an extensive testing and certification. So both the fields are more on to the testing and certification level. So for that, you need to have a very good process, and for the materials as well as the process of the part building. So here we have materials. EOS has done a lot of material research, and they have been medical grade materials which are also available on the metallic side and also on the non-metallic side. So the blue ones are mostly used by EOS, and we do have these powders, which is where in case of, for example, you want to have a certification. So the material portion of whatever documents you need or the certification level is already done by us. So you can just go into the process, the part process or the implant process certification. So it is something like you almost gone through 1/3 of your process into your certification. So on the non-material side, you have the PEAK and PA22 and the PA11, which are both used as the on more on the orthopedic side. So I just wanted to show you a few of our PSIs, which I was also being a part of these right from the design level to the implanting stage. So more on the cranial side, these are the few cranials I think you people would have been seen a lot of on these areas here. The major advantage here with us is the osteo integration. So the osteo integration, you have the softwares which you can use, where you can have the porosity of these lattice structures. So this you can control by using certain softwares. What I was meaning was, you can see the porosity here. That means you can increase wherever, if you have the acetabular cups where it is a load bearing, so or it is a knee, or wherever you have a load bearing. When you do an analysis, in that you can increase you can decrease the porosity so that you can increase the strength, and wherever you don't need the strength, you can increase the porosity. So that what happens is the implant's weight gets reduced, so that the patient doesn't need to carry a huge implant in him. And that is also another advantage here with this, is the osteo integration, which heals, which the healing process takes at a faster rate, and also the implant becomes a part and parcel of the bone or the place where it has been implanted. Here and also here you can go up to porosity up to about 70%. Actually, we have done at least this is a bit about 3 years old. So we have done up to about 85 percentage porosity, but still we are able to withstand the strength and whatever the load bearing, the load conditions that the FE analysis is done. It has been done. It caters to that. And here the strut sizes, that means the thickness of this small ribs, we can go up to about 1.4, which is very minimal, and this gives you the advantages of the it's something like your bone structure. You go very close to your bone structure inside the bone. And here we have also done with the TMJs. Just wanted to give you some basically what we did. And also on the dental applications, we have something called as a cobalt chrome, which is again a specific material which is for the dental application. These are few surgery implants that we did, that I was also a part of it. So this was the implant, which is basically a maxillofacial one. This is during the implant, and after the implant, the post-op, after 15 days, you can see the implant is intact. So this is on a cancer patient. So this is again the implant. What we did was here this implant was a bit thick, so we wanted to use some kind of honeycomb structure inside, and then we removed all the powder from inside, and made the implant a bit lighter, so that it is easier for the patient. And also on the jaw, the mandible basically, and here you can see again, this was one way. This is the initial level of our design, but later on we tried to use, instead of these holes, we tried to use a lattice structures where we had a very light, because the jaw, the problem was the jaw was opening automatically because of the implant. So to make sure that the implant to be lighter, we used lattice structures over here, so that the patient doesn't have. So here again one more implant, which was on basically a tobacco, based of the tobacco. The cancer was being found, and then he had to be used with the implant. Not only implants, we can also do direct instruments with the metal machine. So we can directly do some kind of a special purpose tools. Then the second one would be the machining capabilities. That means how during the process, what are the processes that it is taking care, and how this process is taken based on the certifications that you need to know, or what you have to undergo. Then finally, to do a mass production, you need to have, because in metals you have a support structures. How do you eliminate those support structures so that you get the output more, so that the cost per part comes down? So these are the three things which are very important for a production level on the rapid on the implants. So here we do have the materials. So here we do a lot of partners who do materials. Basically, we get materials based on our requirement, which is required for the medical industry. Then there are a lot of tests which is undergone, and then we also do something called as a inspection certification, and we also, this certification is widely used for the certificate level for the materials. So, and then the system, that means the process. What are the information that you need inside the process for you to get the certification? So these are the details that you can get from the machine as a process, as a document level during the process of creating the parts. So be it the laser detail lead, the process chamber, the details, or the scanning, and then you have the recoating. How good is the recoating? Then you also have the axis movements. So these are some of the things that is being required during the certification level. All these informations are needed for the final certification to be got. So then come to the machine capabilities. So we have somewhere on more than around about 25 to 30,000 data points that you can take for your certification level. So we give data points at every level, right, be it right from the material level to the part level. Here, the documentation is basically used for your certification process, so that which reduces the cost, because you have, if you have to do these all these data points, then it is going to cost you. But we have softwares, we do give you along with the material, we do give you these certificates, so that the cost of your final product would come down. So how do we do this process? We during the process, or during the part is printing, what is that happening? So we have something called as a OT, which is called as optical tomography, where there is a camera, and then this camera captures the heat and also the data of the entire part, and it just stores at a place where you can revisit, and if you find any issues on during the process or after the process, you can reject the part then and there. So you don't need to do a particular test. Then when it fails, or when you do a kind of a scanning, or a thermal scanning, anything like that, so that, or a CT scan, so that you can see any flaws inside. So all that is, you can catch hold of all these errors at the printing level itself. So what happens, you can save a hell of a lot of time in redoing the entire part. And one more thing here is, this also can be used telling that this part is fully is not any defect, without any defect, during the process of your certification also. So this, how is it done? So we have three units which is being used. One is the camera unit, which captures, and we have a sensor which also have a software, and also a separate system being installed along with the system, which will capture all these data, and it will give you the details at a live. You can also see it when the part is getting printed. So once that particular layer is finished, it just stores all the data. So you can go layer by layer and see how that particular layer is being printed. So this way you can get the part porosity or the part defects, everything on the live when the part is produced. So also we do have a lot of monitoring tools, which is at the powder level, that is the powder bed level, then at the melting level, that means when the laser is melting, what's happening to that area. So whether there is overheating or there is a cooling happen, so whatever it is, it also tells you all the information with the melt port. And with this information, with the OT, the optical tomography, you can detect everything, whatever the parts, whatever the implants that you have produced are defective or non-defective. And finally, it also gives you in a report form, based on your kind of, it can be customized based on how you wanted to have whatever is the requirement for any certification that you're going. Particularly based on that, you can get a report based on that certificate. So it's a comprehensive document with more than 25,000 data points. You can customize them as per your requirement. So this brings up to the quality and also the machine capability. Now we'll see how you can get the number of parts, because if you have a big volume that you have to produce, that means in one single shot, how many number of parts you are going to print, that is more important. And how many number of parts needs to be non-processed, that is post-processing is not required. So once you machine it, build it, and then you do a very less post-processing, and then it can be sent for the production. So that is something where you can go hurdle, which is called as your support-free production. That we have. I'm just giving you one example on the hip stems, wherein you can just create the on the right hand side you can see this one. You can just, it's a gap of a 0.3 mm. You can just remove it by using you can use it with your hand force. You can just pluck them like a flower. You can just pluck it. So all these implants are directly, you can pluck it. So you don't need to do any wire EDM or any of the special post-processing activities to get your implant from the build plate. So it is very easy to remove, and it is support free. So then this is also done. See, this angle is done We have done this with the software which is called Amphion for basically it's used for thermal analysis and see how deformation is processed also. So then you can use on top of this, you can do a testing. So in the fatigue test, so this is in the AM implant, this is the first implant which has gone through with more than 5340 newtons for 10 million cycles. And they have found out that this is one of the implants, the material which is done on this particular build. So they have taken this is this it's like something like I have a white paper on this. I can share it to you later on if you want. If you want more details on this, this is one of the biggest advantages that you can have if you are using a hip stem with this particular process. So you can also, it's not that you need to have a solid one. You can directly use, you can also use the lattice structures based on your requirement. So that it can go into, it can be a lighter implants rather than being a heavy ones, depending on your load conditions and depending where you're going to implant the part. So how is done? It is done on this system, which is called as an EOS M290, which is more reliable. This is basically used, and it is a Industry 4.0 compliant system. And we do also have one is called as a 300-4, which is a 4 laser one, which is a 4-quadrant laser. This is considered to be a production system, wherein you have modules where you can see these boxes. These are all modules where once you finish your part, you just load another one and then start the production. So there is this portion will unload all the parts, remove the powder, and it will make the powder ready for the next build. And this is basically the OT, which is normally I was talking about the optical tomography. So everything is integrated in one single system, wherein this can be produced 24/7. The parts can be produced on this. Just to give you a small information on how many cups you can do. So here, just to give you a time, we have different layer thicknesses. Again, this layer thicknesses plays a very major role on how many parts you get in one single build. What would be the fastest time you can get? So on a 290, there are two layer thicknesses. One is an 80 micron and one is a 60 micron. We are also developing a few more layers where you can get much higher less number of hours. You can get higher number of parts. So this is on a 80 micron with the same numbers. So it is about 9 hours. Here you can see 7 hours. So if you're going in for a M300, it's a bigger volume. It's a 400 mm cube. This is a 250 mm cube, and this is a 400 mm cube. So here you can see about 6 hours. You can get about 28 parts. So this is still the medical or the orthotics on the metal. We do also have on the polymer side, based on the PA11 and PA12 materials. PA12 material is a non-splintering material which can, when you bend it, it can come back. It will regain its original position. So then we also done some projects based on the knee orthosis, wherein you can also have the electronics involved. And this is again on the flat foot, where you can create insoles so that if they have a kind of a height differences, you don't need to have a separate shoe for them. It's actually this can also be used in such a way that you can use a height variation and then you can use any shoe. Also on the cranial orthotics, basically when you have a deformation on the baby's head, normally we could see our grannies sometime 80s and 90s, they used to do while during taking the bath, they used to put a hot water and shape the baby's head, but now we have this cranial orthotics. Also on the TKR, when you have the guides, which where it has a lot of parts which is needed for during the operation. All these polymer parts can also be printed. We do use SLS, which is called selective laser sintering, which is basically a polymer where you don't have support structures. This allows us to take care of the entire build, where you can build as a small volume production or a small series production. So this is where I say that we are an end-to-end solution. It's not that we just go with only just give you a machine or the material and then give you, and then we just push off. It's something like our 30 years of experience we want to share with you. So what we do is we just identify a particular technology, or for example an implant. We move that to a business case, and then we try to do if there is a redesign possible, and then produce it to a larger scale or to a production scale. So what happens is, from a normal thing, from a normal implant, you can you can take that implant to production level also. So here we also cater, or we come, we are closely work with you, or we handhold you in many areas, just because that we have people who have been experienced in various levels, be it post processing or be it certifications also. So we do handhold, we support you with all the documents which is relevant, needed for your certification process. So with this note, we take this opportunity and thank 3D Graphy and everyone for giving this opportunity.
Oh, thank you so much, Mr. Ginger. This
You can
was
call me
really.
Sudha.
Hello.
You can call me Sudha.
Okay, Sudhakar. This was really a good presentation. Being understanding all these processes from the orthopedic surgeon point of view, we are really surprised that maybe in India, if there are around 60,000-70,000 orthopedic surgeons, very few orthopedic surgeons are aware about the technological advancements that are happening as far as orthopedic implants are concerned, and as well as far as the orthotics that you are manufacturing. So we will be having a very interesting discussion in the end of the session. Presently, we would like now to go up the chain, where we have the founder of a medical device company, Mr. Sushant Banerjee, and I would request him to. He is the founder of Orthotech, a beautiful 3-decade-old joint manufacturing company in Valsad. And may I invite upon Mr. Sushant Banerjee to make his presentation. Yes, sir.
Yeah, thank you very much. In fact, I am not ready with the presentation right now. I'm right now in some other place. Anyway, it was an excellent presentation, which I think Sudhakar we have made earlier also. And EOS is something which we are also always looking at, and we had a long discussion with them as well. How further? There is a good scope for 3D technology in India, and it is in a very rightly said that it is in a very nascent stage. And what we need is that we need to validate our products. Apart from EOS, I have not seen any other company really validating the products. So that is something which is very interesting, which we'll have to look up to. Regarding joint replacements, apart from what I can say, the load-bearing components, wherever there is a load-bearing sections are there, are we really using that in any other country? Like for example, femoral stem. We are already doing that for acetabular cup, because with the trabecular structure, the acetabular cup is already in use in many countries, and we are already introducing that in India very soon. But regarding femoral stem, I would like to know, is there any white paper on that femoral stem are being used in hip replacements? Can anybody of the panelists help me with the answer?
Mr. Sudhakar, the question is, because in one of your slides, you had shown a very lightweight femoral stem which had scaffolding, and you had given that implant design based on the simulation studies, right? So I think that was an elder product or some company's product. But I think Mr. Sushant is asking that question on basis of that femoral stem design which you had shown in that presentation.
You're talking about one second. Let me just share my screen so that it is one for one. Is this the one that you're talking about?
Sushant, is this the one? Yeah, most probably I think is because this was one unique stem, which you had presented, and if you see a few slides before that, there was a slide based on simulation studies and the
Yes.
load
Actually,
bearing.
this was done in Europe, not in India as of now. But one of our service bureau is doing this STEM, and currently they are into kind of a certification level. So yes, India, we are doing along with one of our service bureau who's actively doing this femoral stem in India.
So is there any white paper or is there any study that has happened from that femoral standpoint?
Yeah, I can share you that white paper. Yes, possible. I can share a white paper on that femoral stem study.
Okay. Can we have Dr. Jayesh and Dr. Sushil both? I think both of them are ready with their presentations, and we all would be very happy to listen to both of them.
Yeah, so Dr. Jayesh sir is here. Dr. Jayesh Balare is the institute chair with IIT Bombay from the chemical division. Sir has been an active respondent in terms of research of various different materials. So it's a privilege to have him, and so kind of you, sir, for having given us your time on a Sunday. But it is a very active participation of respondents from the last 2 days. In fact, in the morning, the dental professionals, the AOMSI members also did mention about hard and soft tissues. So Dr. Girish Rao, he was also expressing that it was a good session. But similarly, in orthopedics also, we are seeing a prospect for collagens and meniscus and scaffolds. The soft tissue, doctor. So Dr. Vikasji, Dr. Jayesh will do the presentation now on the subject. Sushil will.
So I'll also like to tell him that I am an alumni from IIT Bombay.
Yes. I was supposed to introduce you that way. Yes. So
I have a mixed qualifications of being an orthopedic surgeon and a management MBA from SJ SOM.
Yeah.
All my son and my father, all of them were from IIT Bombay, so very closely integrated with IIT Bombay. To have someone from IIT Bombay is always close to my heart.
Yes, great. So
it's great. Thank you. Yeah, that's a great pleasure to have to be amongst your midst, and thank you, Shibu, for calling me at short notice. And,
always a pleasure.
Always a pleasure. Yeah, it's always a pleasure to discuss with with experts like you all, and it's my honor to show you a few slides. I don't think I'll go through a formal presentation, because generally when I present this, I often present it to a mixed audience, but here we are all, I think all are experts. So forgive me if I, skip through some slides and get to the meat of the matter. Shibu, should I show a few slides and then I'll be open for questions?
Please, sir.
Okay, great. So let me try to share. So what I have here is a sort of a comprehensive presentation which covers lots of things.
Perfect, sir.
All right. So let me, I'll jump through a few of these slides, but essentially what we are interested in and what we have been doing so far for the last decade or a little more than that is to look at resorbable materials as scaffolds for bone reconstruction. We have two or three different types which I'll talk to you about, and there's been a whole bunch of my PhD students and postdocs who've worked on this, and we've also had lots of collaborators, some from Tata Memorial, some from All India Institute of Medical Science, and so on. So there's been a large group of us who's been involved in this, and generally we are in the space of biomedical materials across many disciplines, right? Many medical and surgical disciplines. So we look at materials which are resorbable. So first of all, these are materials that are resorbable. We don't want them to last forever. And second is that they are often nanostructured. So they are structured at a nanoscopic scale, which is typical of all tissue, of course. And based on these two important things, we've been looking at many different types of materials here. So I'll just spend a minute on this slide and move on to the bone part. So besides bone, we've been looking at hollow fiber membranes, and these membranes are extremely useful, of course, in hemodialysis. But we have also converted them into hollow fiber bioreactors, and these bioreactors have gone on to make bioartificial organs, such as besides the standard hemodialysis setup. We have also made some bioartificial kidney constructs in the lab. We have also made bioartificial pancreas, that is, we load either stem cells or islet cells into the lumen of these tubes. So these tubes are very narrow, sub-millimeter size tubes like a thread, but they are hollow, they are perm selective, so they are immuno-isolatory, so we can put even xenografts into the lumen of this tube. And in the case of the bioartificial pancreas, we've optimized this with a scaffold structure in which the cells, islet cells, can grow inside, and we've used both pig islet cells as well as human mesenchymal stem cells differentiated into islets and implanted them into an induced diabetic model in mouse. Did a study for about a month and showed that normoglycemia was established in a diabetic model of the mouse. So these are materials which are extremely biocompatible. In this little diagram here, it shows that these fibers have got incorporated. There's been a lot of blood vessels that have been laid around here. So these are extremely biocompatible materials, and we are also using this now to make bioartificial liver and other such constructs. We also look at materials on the top right corner, which are used for minimally invasive surgery, especially of the heart, closing holes in hearts, PDA and ASD closure devices. And on the middle left, we look at nano medicines. These are nanostructured medicines across all systems of medicine. We've made a nano carboplatin, which has been used for retinoblastoma. We also study what happens in other systems of medicine, such as Bhasma in Ayurveda, homeopathic nanoparticles, where some of our work has been very recognized very well across the world. And we also make these membranes used for guided bone regeneration. So this is sort of canvas of a variety of materials, but now I'll focus on the bone reconstructive materials that we've been looking at here. So some of this, of course, is elementary for this audience. But let me tell you what our solution for these moderately load-bearing structures is a 3D printed construct, which can be made either in standard shape, so there can be some stock of it, as well as it can be made into a 3D printed customized shape. And I'll show you the workflow in a moment of what we do. So unlike most materials which are 3D printed for surgery planning, these are actual implants which can be put inside the body, and eventually these are resorbable. So some of this work we have begun with in the dental and maxillofacial space, but now long bone is the focus of our interest currently. So our attempt has been to try and mimic at various size scales the structure. So jumping ahead, what we are trying to do is to mimic the entire chain of structures right from the external shape. So if there is a closed fracture with loss of some part of the bone, you can use either a standard shape, or we'll take a CT scan and customize it. And then we also mimic the cancellous nature, the interconnected nature, down to the trabeculae, and then even to the molecular structure, which is of course collagen in the case of bone. What we use is gelatin, comes from collagen, and the reason to use that is much simpler, much cheaper, works equally well. In fact, in some in vitro and some early in vivo studies, works just as great without having the problems associated with collagen. Yeah. So when we start making these bone scaffolds, numerous properties have to be satisfied, and I won't dwell on these. I mean, essentially we got to satisfy lots of biological properties, lots of structural features, and we try to mimic as much of them as we can. The materials that we choose have to be special. We don't use metals in our constructs. However, in using some of these, if it is a highly load-bearing structure, a little bit of metal may be necessary, but the large amount is replaced by polymer and ceramic mixtures, all of which are resorbable, biodegradable. And we need, of course, special fabrication techniques, including some that we have developed ourselves, the gel printing technique, which I'll talk about in a moment. And sometimes we need to use a combination of these techniques. So we don't rely on a single technique, we use a combination. And then the goal is to, of course, have good cell viability and attachment, good osteogenic differentiation and cell proliferation, while having good host integration, vascularization, and some degree of load bearing at least. Yeah. So these are some of the properties we try to mimic. These are, of course, well known to you. I won't go through this list, but we do want to have the porous structure, ability to degrade, some amount of strength, customizable shape, osteo conductivity, and perhaps osteoinductivity as well, yeah. And controlled degradation. So it just goes away after some time. So there's nothing to worry about after a few months. Yeah. So the general things that we are looking for in this is to try and make it patient specific. If you look at the bigger picture, patient specific is great in certain cases, but you also need some standard shapes so as to be able to provide patient relief immediately. Then one needs to have a porous structure. One also needs to have a graded porosity from the cortical cancellous structure that is needed to mimic the biology as much as possible. Point number 5 about adding cells. Yes, we have we've tried a few experiments by adding cells, but then there is a lot of regulatory issues if we try to add biological cells into a scaffold construct. So at the moment we are although we are doing it in the lab, we are not promoting this for patient use at the moment, but surely this will change as the regulatory scenario improves. What we find is that our constructs are extremely osteoconductive, even a bit of osteoinductive. Therefore, they are very they don't need this cell construct. Some degree of load bearing versus the biodegradable nature. And lastly, how fast for a custom made one, how fast a turnaround can be provided so as to be able to do the surgery as soon as possible. Yeah. So based on this, we have developed several such products, materials as well as products. So these are all new materials, and that is a benefit in some sense, and it's a disadvantage in another sense. The disadvantage is that it has to go through a very rigorous regulatory procedure through drug controller, CDSCO, and so on. So that's some hurdles there we have crossed, and I'll get to that in a moment. So the products that we have are a sponge. It's like a gel foam, except that it is highly osteoinductive, and this is a nanocomposite structure. It has the trabecular-like structure. It can be like a sponge. It can be stuffed into the narrow neck of a bigger opening, which may be underneath, and it promotes bone growth. And there is some micro CT data which I'll explain in a subsequent slide. We then also make bioresorbable screws. These are screws made out of a special blend of magnesium oxide and silk fibroin. And what these would be useful, particularly in sports medicine for ACL repair and so on. So these are now undergoing preclinical trials. The bone graft is undergone first in human trials, and I mentioned a little more about it in later slides. And then we combine some of these technologies to produce these 3D printed scaffolds. And here is a little piece that we have made to mimic part of the jaw that's going to be excised in a cancer patient. And for long bone, if you want to fill a gap, it's possible to fill this with a hard material which has both hard and soft built in. So the gel is built into the hard matrix. Both of them degrade. The gel causes osteoinductive behavior so that the construct fills with cells as they grow. Mineralization is done naturally by the body, and this the harder scaffold degrades over a period of a year or so, and therefore eventually the original scaffold is completely gone. And then we make these nanofibrous membranes as well as those are useful for guided bone regeneration. All of these have nanohydroxyapatite into them of varying concentrations, so that it provides a degree of osteoconductivity which is not there in many other such scaffolds. So for customized products, we see the workflow beginning with a CT scan, the defect isolation, and then making the doing the 3D printing of the hard part of this tissue, and then checking the fit, taking feedback from the surgeon that it's okay, and then actually print it. The hard tissue is then filled with a soft gel. The soft gel provides the osteoinductive nature, and then it can go into into the patient here. And this week we are about to begin. So this has all been tested in vitro. We are now beginning a preclinical first in animal experiment in rabbit tibia of this experiment, and soon, as soon as we get a clearance, then we will apply for to CDSU for a first in human trial. So these are totally biodegradable material, limited amount of load bearing. Will at the moment need a small plate to maintain it, but will cause the gap to get filled very quickly. And the performance of this is proven by this sponge material which we now have, and the same sponge material fills the gap in the hard tissue that in the hard scaffold I showed you in the previous slide. So this particular spongy scaffold, a bone void filler, has undergone a first in human trials. It's approved now as a pilot study, and it shows what happens. And this is a rabbit study which we had submitted to the drug controller for approval. So let's look at these two this part of the slide. In these two panels we can see this sequence here is the treated side, in which there was a bone defect created in rabbit tibia. It was then filled with this bone void filler, the sponge which we have, and whereas on the in a control test, it was a sham test in the sense there was no graft put. So we can see on the sham side, there is bone being laid and there's bone remodeling happening, but being a critical size defect, the gap is never bridged. And whereas in the case of the treated side, not only is the gap filled, but it's built up to high bone density, so that the bone is restored in a quick and efficient manner to a relatively high bone density. So that's the performance of this material, and this is a micro CT data, and similar results have also been obtained in other with other constructs such as this GBR membrane, which was used in a rat calvarial model for cranial surgery. So these have all been published, and now this is the data which convinced the drug controller to help us do this in human, and we've finished that trial at AIIMS New Delhi. So first in human is over. The pilot study is very successful. The surgeon is happy with this, and now we are trying to get permission to take this ahead. As you know, for it's like a new drug application. It requires some time, lots of money, a lot of persuasion, and you've heard about problems with getting some of these in the very last week of getting such approvals done quickly. So these are things that we are currently struggling with. So these micro CT data really has been the clinching evidence, which tells that we get very fast mineralization. These are resorbable, and they are safe. And then on the biology side, we do all these studies to ensure that there is a good cell attachment. So integration with existing bone is there. There is good activation for mineralization through these osteocalcin labeling studies. And therefore now what we are now doing for us to mimic this entire nature of going from a dense bone to a hollow bone by building constructs of this sort, not only standard shapes such as this cylinder here, but even odd shapes like this. So we've we try to make this natural bone gradient from outside to inside, so that it will mimic, it'll give strength as well as mimic the natural structure. This is, of course, well known to you all. So in order to do this, we have built our own customized 3D printer in which the gel is printed, and the gel is printed into the structure of this hard scaffold. I'll skip some of these details here, but here you can see the results. These are electron microscope pictures of our scaffold, which shows both hard and soft tissue built in, and eventually we have the microporous structure, and at a nanoscopic scale, each of these has got it has got the polycaprolactome and gelatin along with the hydroxyapatite and nanohydroxyapatite within the trabeculae of these structures. So that's what provides this osteoinductive capability, and it also this entire construct is spongy. It is flexible. It recovers. It can be compressed and pushed into a closed space, and it will expand and fill out. So that's another added advantage of trying to push it into confined spaces. Again, we do microscopic studies, and we hope now that we are able to provide some patient-specific 3D printed products. The workflow is already done. We take CT scans in our lab, do the defect isolation, use a computer artist to provide a solution that gets an okay from the surgeon, and then we print it and give it back. So the workflow is there. We are, of course, waiting now for approvals. The whole slew of drug controller approvals by virtue of the materials being new and the combinations being new, the technique also being new. So everybody is wary about this, and naturally so. We want to ensure that it's safe. But our first in human trials at AIMS show that it indeed is, and this product with its gelatin and other constituents works very well. Yeah. So that's where we are, and we are looking for, these are some actual patient data that we've tried to look at. So what we've done really is from a technical viewpoint, we have these new algorithms for the gradient. We are able to make these complex shapes and generate this gradient porosity, and we've proven these in the lab, and in some of our samples we have proven this in human. We have permission for human trials of a pilot kind, which we've completed. We are now waiting for pivotal. A multi-center trial is what we want to do next, and that's really where we need your help and advice. I would be very grateful if some of you came back to me with a willingness to try this in 10 patients with following a typical protocol, particularly for maybe for a long bone, either closed or open fracture, where we would like to make this construct either in a standard shape or a customized shape, and see that it works. So let me stop here and hear your comments and advice. Thank you so much.
So, Dr. Bellare, being an orthopedic surgeon, this is something very exciting.
Great.
And you would be surprised that I'm a part of the past president of Gujarat Orthopaedic Association, and we had the orthopedic surgeons from Indian Orthopaedic Association. And with additive layering and 3D technology, and with you having a product which is going to mimic a bone which has an osteoconductive and an osteoinductive potential, I see a huge disruptive demand that this particular product would have. So I can also understand that there are challenges that you're having. You're already given permission for human trials. We'll see to it with Dr. Shibu. Thanks to you to have introduced us to Dr. Jayesh. I will try to integrate you with Indian Orthopaedic Association, so that with the required permissions that you have for human trials, we can have very dedicated orthopedic surgeons from Indian Orthopaedic Association across India who are innovative and who would like to support this study, because this is the future. Ultimately, what I understand is that we as an orthopedic surgeon understand the challenges that we have as far as tumors in the bones are concerned and as far as trauma in the bones are concerned. And there are times when we do not know how to give an optimized anatomy and physiology to the patient when the patient is about to lose his bone and part of his musculoskeletal system, right? And with additive layering technology, now we are thinking in terms of getting very specific implants. And now you have again given us a resorptive, osteoinductive and an osteoconductive solution which can be 3D printed, which can act as a scaffold and which can enable a new bone growth, specifically using an undifferentiated cells or using cells from BMAC. I don't know why you have issues using BMAC, because we are into regenerative orthopedics, and in regenerative orthopedics we are also using PRPs, we are using bone marrow aspiration concentrates, and these have in a concentrated form have got huge potentials to regenerate bone cells, osteoblast as well as chondroblast. So I would also want you to start thinking in terms of doing something for menisci and also doing something for cartilage. So when you're talking in terms of a bone tissue, my whole, because you are from the IIT and you are into the biomaterial, you are into the nanotechnology, these are the things which can be worked up and this can be researched. So it was really very interesting, Dr. Jayesh. Mr. Sushant is also there from Orthotech. I think he would have found this very interesting. Both of us would love to visit you to IIT Bombay. Dr. Shibu is also there. And I hope a lot of delegate orthopedic surgeons who are watching this across India also would have found this very amusing. So thanks a lot, Dr. Jayesh. Dr. Shibu, would you like to add something?
In fact, I'm an added fan of Dr. Jayesh sir. He is doing some great work. In fact, last year when we did this conference, I had Dr. Lalit Maini sir. Doctor,
he's another researcher. Yes.
Right. And he was actually in the quest of wanting to know about this hydroxyapatite, whether it has been done. So, doctor he set a pathway saying that we're doing it ourselves. We're also doing our bit, a set of research. So, I'm saying there's so much of things happening indigenously by these wise intellectual respondents from each of these institutes, which probably have really gone untraced, maybe, So that is where I'm so privileged to have experts to all come together and see, where these gaps can be filled. So I'm so happy because I could, set the pathway in terms of connecting the right chords to the right people. And I'm so excited with the kind of work that doctor has been doing. I mean, it needs to be seriously commercialized and we need to promote it. And that's the beauty, sir. I mean, that's where I see, because clinicians are doing their bit. They are doing some great work. But they're probably not getting that time to probably exercise and get to know what is happening in the closed doors, what researchers are doing when it comes to some great work. So I think that is very, very important. Now that we know that these all things can be done, I'm sure I can see in your face the excitement. You're also a very passionate man, Doctor. I know, Dr. Vikas. You come with a lot of zeal, want to know about the technology.
I'm happy. We will take this research to the level that Dr. Jayesh is thinking,
Yes.
And whatever challenges that he is facing, I think Mr. Sushant is there, and we, Dr. Shibu, you are there. So we all will be together, to enable, whatever constraints that are there, because this is for the best of the mankind. This is for the good of the mankind, and we should all
exactly the same thing that was actually expressed by the other senior leaders like you. Also on the particular subject, because it needs to be seeing that how it can be benefiting. It should be socially it should be for benefiting others, and so much of good work already been done. So I'm so privileged to have a good set of a panel like these and also connected. So Dr. Vikasji is also from the advisory now for 3D graphy, like you, sir, from the research and material science. So that's the beauty of it all in terms of having been able to construct this.
Shibu, Shibu, give me, just give me a few seconds to, of course, thank you and thank Dr. Vikas for his comments. I'll just respond to the PRP and VMAX and other things. We are very enthused to do that, but that has to be done at the clinical level. So we would love to do this in your lab, where we can do this. This is not something we can do at IIT or in our lab. So that's where we need to work close together. So so when we look at it from a commercial viewpoint, I cannot stuff this with cells and give it to you. I mean, you have, that is something that that we have to work together to do in your lab. But yes, I think that is the future.
I
The
would
bioprinting is the future.
I would like to add something. Dr.
Yeah.
Jayesh,
Yes,
good
Sushant,
evening, sir. How are you?
I'm very well, sir. Thank you. I remember last year we've met a few months back on
Yeah.
this platform. Thanks to Shibu, and
Right,
your advice and help is always welcome.
right.
And thanks to see you
Yeah,
again. I
yeah,
see Piyush
yeah.
also there. So I think this is a
Right.
great group. Thanks, Shibu. Yeah, Sushant.
Sir, there is a good news that we are making a consortium. Dr. Vikas is there already, as an advisor to Orthotech, and me being a manufacturer and you being a researcher. Let us build up a consortium which we can take
Sure.
the benefits to the patient. So that is the basic idea of us, so that we can build a consortium where the orthopedic surgeon, the researchers, and the manufacturers like us can build up a consortium and take the benefits to the patients. So that is where my interest will be, and it will be our interest rather to take it to the patient, the best of the products researched in India, made for India, researched in India. That will be the great thing. And we are
Absolutely,
always there,
Sushant.
and I'm
Mr.
really
Sushant,
very happy.
as an Orthotech owner, I would request you for enabling Dr. Jayesh for whatever small challenges that he has. We can together meet him personally
Yes,
and help him with all those challenges.
Absolutely.
Very
You have
soon we will,
let's have a
very
meeting.
soon
We'll
we'll meet
organize
up.
a meeting. Yeah, we'll
Yes,
organize
sir.
a meeting maybe in July at IIT, and we're very happy to host all of you. And let's see how best we
Yes,
can take this ahead. Thanks a
Sure.
lot to
we can
everybody.
take it.
Yeah,
Sure,
thank
sure,
you.
sure.
Thank you, sir. So one more thing that I wanted to know from you, sir. Now we were discussing on the approvals on these patient-specific implants. See, the modular implants are always, there is a standard process to follow. So everybody is aware that there's a process to follow, and doctors have been able to use this. But when it comes to patient-specific implants, we were also discussing with Sudhakar and Rajesh and various other technology experts who are actually also in the business of suppliers and OEMs. Offering solutions when it comes to machines. Now, in patient-specific implants, now that is the question which Sushantji also had, that the patient-specific implant, the approvals and the and accreditation like an FDA or maybe a CD ESCO needs to be acknowledged. I mean, that kind of an approvals need to come from these valid bodies. So how do you think a patient-specific implant? I mean, it will be very similar to what you are doing, sir, right now when it comes to soft and hard and
Yeah,
soft tissue.
it's absolutely similar. In fact, we are now, grappling with this exact problem. That is, we are talking to the CROs to see how best we can get the broadest possible approval from CDSCO to cover, to cover a whole bunch of conditions or indications rather than specific. It should be something. It should be a process of manufacture. It should be material. It should be indication. So, and these should be as broad as possible. So this will be tied into the process of manufacture tremendously. Therefore, machine manufacturers have to be involved and be there. So I'm glad Piyush is also here. There are of course we need other types of material suppliers also to be present, and we need the clinicians to guide us, because it is ultimately their colleagues on the expert committee that of CDSCO sit typically the orthopedic surgeons and dental surgeons and allied medical professions. So we need to make sure that group is convinced that we are doing things safely. Ultimately, what we have to the regulatory process is something we are navigating ourselves. So I have no complete advice to offer now, but I think within a few months, when we are passing through this, we are about to file one application to do this. Let's see how that works out. I think we have some basic idea that it is the process along with the materials involved and a set of indications together that will receive the approval. So that's probably the way to go.
So then a pathway will be set, for others to follow. Yeah. So that is important. Dr. Vikas, any thoughts? Because we were just discussing on that. So Dr. Jayesh, we have all the material companies as well as the metal companies also here. The polymer also is there. Software companies. So that's the platform that we are in. And also with Piyush coming from his area of expertise in terms of soft and hard tissues, in terms of bioprinters. So we are all here. What we will now do is we have Piyush also joined to share what he has, to share on the subject on soft tissues that he is working on. Piyush was there in our session yesterday, which was very specific to hard and soft tissues. It was on 3D bioprinting of hard and soft tissues for different medical specialized applications. So, Piyush, if you can share your presentation, I think then we're done, and then we will have a small, discussion, of each of these aspects.
Sure, Shibu. I'm just going to share my screen. Just give me a minute. Just loading up the presentation. Hi, Shibu. Is my screen visible?
Yeah, it is visible. Piyush, please. Thank you.
Okay. It's the same presentation as yesterday.
Yeah.
Nothing new.
No, I think the audience here is different, so I think relatively they'll be able to learn about this.
Okay, great. So, hi everyone. This is all last minute, but yes, I think I'll just give you an introduction about us at Next Big Innovation Labs, what we do, and who we are, what we've been doing for the past 6 years in the field of bioprinting. So, we consider ourselves to be a deep tech 3D bioprinting company. We were founded in May 2016, around about the time when Shibu also was starting Trinity. And we basically work on 3 levels of bioprinting. One is developing the technology, that is developing the key 3D bioprinting technology, the 3D bioprinters as such. So we use patented versions of these machines to develop 3D bioprinted human skin. Right now we are working on the human epidermis. The application of the human epidermis is primarily for, as an alternative to animal testing in the cosmetic, chemical and agrochemical sectors. But the long-term vision for the InnoSkin brand is going to be 3D bioprinted skin, probably a full thickness model which will have the dermoepidermal junctions as well as the dermoepidermal portions in for clinical translation. So that's what we envision the brand to be. Obviously, we are not only going to look at skin. We are in the future hoping to collaborate and work with clinicians as well as researchers to build specific functions of the skin, such as sweat glands and hair follicles and all of that. But one thing that we noticed was, during the course of our journey was that, the awareness about 3D bioprinting, its applications was lacking. And that's when we started Next Big Learning. So this was started during the pandemic period. When most of our teams were sitting at home and, we had a lot of data and we thought, this is the right time for us to build something that could actually educate people in the domain of 3D bioprinting. So under the Next Big Learning banner, we try to build awareness about the technology and how the technology can be applied across various sectors. Most of you might know the process of 3D bioprinting. So you have something called a bioink, which is basically cells, biomaterials, and nutrients. All of these are mixed in order to form something called a bioink. Now this bioink is deposited layer on layer, like you can see here. It's one layer on top of another that's being deposited here. Basically, given the factor that we are able to control the deposition rate, we are invariably able to control the number of cells per square millimeter of the scaffold, thereby creating tissues that are more that are more optimized, or tissues that are more uniform. Is much more easier using this technique. And obviously, after you build the scaffold basically forms the initial sort of nutrition for the cells in an in vitro setup. And over a period of time, the cells start to migrate and proliferate, and they start forming their own ECM. And finally, the output that you get over here is our InnoSkin product, which is just as thin as the skin from your lip. It's the human epidermis that we have printed. Now, the primary application here, like I said, is as an alternative to animal testing. But we want to go one step further and see how we can, get into the clinical aspects of bioprinting as well. So there are many applications of bioprinters as such. Like I told you, tissue engineering is one of them. What Dr. Bellare is also doing in terms of biomaterial studies, research, as well as to understand, how the biomaterials and the tissues can actually, the cells can actually go together in order to form holistic tissues for transplants. That's another thing as well. But then this was the promise that 3D bioprinting started off with. Now there's a long-term vision. Obviously, the holy grail is to see how the technology can be translated into a clinical aspect. But there is a lot of research apart from that can be done using the technology. The technology can impact various sectors. I'm just going to start with cancer research because it's one of my favorite topics. So in cancer as such, there is so much that we can do. We're understanding the disease year on year. There are more innovations and applications that are coming out for cancer. But specifically, what bioprinting can do is to help us better understand the cancer microenvironment. Yes, it varies from patient to patient, but we can develop certain almost close to standardized models that can be used specifically for. Can be used for drug development studies. It can be used for personalized medicine, as well as to understand how a specific drug or a treatment is reacting to a specific form of cancer. The next one, which was very interesting for me, was bioprinted meat, where people are looking at how they can print meat not only for sustainability on Earth, but there's a company in Israel called Aleph Farms that is basically bioprinting meat for space. So this is going to be a huge game changer if they are able to do it. But these are some of the applications of the technology. There are a lot more that I can delve into, but in the interest of time, I'll just move forward. So we, like I told you, build bioprinters. We build high-tech 3D bioprinters from the ground up. Here what you see is a dual extruder print from one of our Trivima bioprinters that is right now at Central Leather Research Institute in Chennai. So as you can see, this is a dual extruder print. So you have pneumatic pressure that is specifically controlling the deposition of the liquid on a heated bed over here. Here, it's obviously you're printing it one layer on top of another, but only thing with two different biomaterials as such. So this is the basic core concept of what 3D bioprinters do, and obviously there are different technologies that allow you to do so. There is a high level of customization. Obviously, like we are working with different kinds of biomaterials. We are working with different kinds of cells. So what we did was we wanted to make it easy for researchers. Initially, when we were doing, in 2016, when we were speaking to a lot of researchers in the space of bioprinting, what we came to understand is that the customization options were minimal, and we were actually planning to buy a commercial 3D bioprinter, but the feedback that was given to us was to actually start building one on our own. And that's when we started building our own 3D bioprinters. We had to customize it for the team working on the skin projects, but then on a macro level, we customize how many extruders you can work with. That means that translates to how many different cell types or biomaterials that you can work with, especially when you're dealing with complex organs. You would need different cell types to be printed. The other one is temperature control, where we go into cryo temperature control, as well as up to close to around 125 degrees centigrade on the extruder head. And then we also build in the sterility options within the printers. There are different ways. Obviously, there is more micro level of customization that we do. But one interesting project that I want to talk to you about is with Merck. So in 2018, we got to be a part of the Merck Accelerator program, and as a part of the Accelerator program, we got to discuss with multiple teams within Merck to understand how the technology can be utilized within Merck, and how Merck as such is looking at the technology, up and coming technology at that point of time, as like 3D bioprinting. And we got a project. The first goal of the project was to print these drops. Basically, we had to print close to around 10 microliter or a 15 microliter droplet. Specifically, just put a drop and in the middle of every. This is a 96 well plate. We also had to do it for 384 well plates. We achieved this with Merck, and this was used for tumor modeling studies, where they would, create these mini tumor models, and they would basically run different drugs on them to understand how how the drug is specifically affecting them. Then they said, okay, you know what? We want to do something called co-culture studies, where we need you guys to print one drop, like you can see the blue drop over here, and then we need another drop on top of that, which is a totally different biomaterial. We were able to achieve that as well. That took some crazy engineering, and that's what led to our first patent, which was the anti-backlash system for specific control, movement control within the system. Then we thought, okay, the worst is done, and then they said, no, wait. You guys need to print within the well. We need one line beside another line. And the diameter of this well is close to around 0.5 centimeters. So within a 0.5 centimeter well, we actually had to draw two lines side by side. We were able to achieve this as well. This is where we actually saw the power of customization of bioprinting. How technology needs to be customized in order to derive certain specific results for a certain specific industry. Customized engineering, even in yesterday's talk, a couple of my fellow speakers were speaking about how customized engineering has to be the solution, customized materials has to be the solution, and customized implants has to be the solution. And all of this technology plays one role in this entire ecosystem, and we are trying to see how we can build customized solutions for researchers as well as for clinicians. So we've worked with a plethora of biomaterials, right from a mixture of synthetic and natural polymers. This is a PCL and gelatin, which was printed in various hexagonal structures of different layer heights, and they basically wanted to understand how basically breast cancer cells behave in different environments and how they interact with the normal cells as well. And then another interesting one that we did was a bioceramic one, where one researcher in Bangalore had given us a beta TCP and HA slurry and asked us to print it. We were able to actually print it. It took a lot of R&D, but that led to our second patent, where we were able to develop a precise temperature control system for the extruder, and that allowed us to actually print the bioceramic in question. So we have also we have printed with light-based biopolymers to create these cylindrical structures as well, and we also go highly intricate because of the anti-backlash system. Our patent that we have developed, we are able to actually go very complex in terms of the structures that we are able to print. So Dr. Bellari was also mentioning about gradient scaffold structures. So these are something that we tested out our machines with in 2018 itself, and it was for us it was a good sort of validation of the technology. With Rivima, obviously we work in a 360-degree format because, like I said, customization is one thing, but support is also going to be critical, and that's why we try to see how technically we can support researchers and clinicians who want to work in the space of bioprinting. Along the way, we've had some key technology partners. We've had Autodesk that provided us with all the softwares, and then we've had Microsoft. Microsoft has been a very key partner for us since August 2021. We have developed an AI-based bioprinting platform with Microsoft. So basically, what we are currently doing with Microsoft is we are taking different scaffolds and basically classifying them into good, bad, good, great, and bad. So basically, under extruded, like you can see here, optimally extruded, like you can see here, as well as over extruded, like you can see here. So based on this, we were basically classifying these scaffolds, so the printer will be able to think by itself and basically develop better scaffolds based on a biomaterial input, as well as the kind of cell type you're dealing with. This is obviously has very good translation towards the clinical side of things, where you're looking at developing scaffolds that are more uniform in nature, and that's what we are trying to achieve with Microsoft. Yes, we are going more crazy with the algorithms, and we feel over a period of time that's going to improve. But yes, we've just started on the project, but we have got very good traction over the past 8 to 9 months with Microsoft. So with that, I'll just end my slide with this. We at NBI look at ourselves as a platform company. The team, technology, process, patents, all of these form the basis of who we are. Trivima, Next Big Learning, and InnoSkin are already products that are in the market, but we also collaborate and consult for researchers and clinicians who want to get into the field of bioprinting. And we always want to see how we can develop novel, customized technology solutions for both academic researchers as well as clinicians who are interested to develop novel solutions. So with that, I'll end my slide here. Shibu, I think if I'll take any questions if required.
Yeah, thank you, Piyush. Again, from the orthopedic point of view, we were, because this being predominantly orthopedics, we were predominantly interested more into the soft tissue bioprinting that you can do or think ahead. As yesterday I was mentioning, for the cartilage as well as for the soft tissues, predominantly the muscles and the collagen, right?
Yes.
Ligaments.
Yes.
So I think somewhere if you can also think with the type of work that Dr. Jayesh is doing, where he is using nanotechnology, he's using biomaterials. I think even you can also think in terms of you having those technological biomaterials. Ultimately, I'll tell you why as an orthopedic surgeon this is important. This could be very disruptive because we have patients in trauma as well as in degenerative joint disorders where there is a lot of damage that happens also to the soft tissues, also to the cartilage, also to the bones, and there is a need where we can do a lot of replacement. Now, that is where the challenges always would come in every orthopedic surgeon's clinical practice, in their surgical practice, and the researchers like you will have to start thinking in terms of coming up with solutions.
Yeah, that's basically what we're doing. So for skin-based applications, I didn't mention today in the talk, but we have developed a novel biomaterial which we're keeping currently as a trade secret. We are still studying it. We found some good applications of it, and we're trying to explore how it can be used for cartilage as well. But yeah, that's one of the areas that we are interested in. We want to work in that direction as well. I think in terms of bone, cartilage, meniscus, I think there's a lot of applications, sir, and we as a company are looking at clinical translation. And I think the first line of us even getting here is to have discussions with clinicians who are day in and day out dealing with these kind of scenarios, and develop solutions based around that. And that is something that I think we will be starting soon as a team. The focus is to start it within the next 6 months because we have the InnoSkin product launch as well this year. But we are looking to start. We are looking to get into that line as well.
A good idea also would be to integrate yourself with the orthopedic community, in order to understand what are the challenges and what are the exact type of products that you should research on,
Yeah.
Because anyone has to say something,
Yeah, I have one question. I'm Sushant from Orthopaedics. Yeah, Piyush, your presentation was really interesting and very impressive. Okay, we are manufacturing implant with hydroxyapatite coating. Okay. There is no way to test whether the bonding with the muscles are taking place at what time and to what extent. Okay. We are following certain technology which is there already. But we would like to know if I want to test, if I want to change the parameters and to check whether the bonding is happening or not. Is there a way out where you can help us? Instead of, I cannot try it on human beings. So can we try it on these cells?
Yeah, I think we can develop a model that will, sort of allow you to figure that out. So I think what we can do is, probably I'll get my scientific team also included, and we can have a discussion where we can go in depth to actually understand the problem. And I think there's a solution that can be developed. I'll just give you an example of how a medical device company had reached out to us. specifically to understand, if they puncture the skin. They were developing a device that actually punctures the skin, and they wanted to understand if I puncture the skin using this needle, what would be, the rate of when you're looking at the skin cells actually covering up the wound, right? In the epidermal layer and the dermal layer, what would be the damage caused, as well as what would be the rate of recovery. So that was one interesting study that we were a part of, and I think something similar that you're suggesting, and we can have a discussion on this, sir.
Has been the question
So,
always.
and is there anyone on the panel who would like to ask more questions? Dr. Shibu, would you like to add something?
Yeah. So, so Piyush, what we are looking at is in terms of various different applications.
Yeah.
Now that you are also a key respondent of 3D graphy,
Yes.
where I'm also coming from is, this being one of the areas wherein actually Dr. Vikas also mentioned, in terms of the requirement, in terms of where we can see and fill the gap of various applications. He is more an expert to share with you. What we are trying to do is with this kind of a module, let us have a constant kind of a communication.
Yeah,
It
I
should
think
be an
that's
ongoing
important.
constant communication. So what we've done as a platform, what we can do is something very similar is what we did recently. It was an hour and a half session, very specific to the T in terms of what was expected. It was on antimicrobial materials. So Dr. Vikasji and the entire orthopedic team, or the senior respondents like the Honorary Secretary, IO, and also Sushantji, and even Swarupji, if you know, Swarup from
Yeah.
Androtech. So all of them joined and discussed and understood what this technology materials can do, and where all it can be used for applications. So this was he's a gentleman. He's also a 3D graphy associate member. He joined from Chile. He is supposed to join in the next session, the track 7, and I will invite all of you gentlemen to also join that session. Though you will not be on the stage, you will definitely can understand and learn what are the various applications used. So Dr. Claudio Soto will be joining from Chile, and likewise other orthopedic surgeons and onco surgeons will talk about precision in terms of what is required for sarcoma treatment. How and what are their challenges. So that is where we need to fill in that kind of a gap. So what I'm trying to say is we can do a series of these and try and understand what is the requirement. What doctor did mention, we will try and see and see that key respondents like you can also be a part of that particular ecosystem to see what is the problem statements of the doctors to come up with solutions accordingly. So
So we are. We are actually, Shibu, sorry to interrupt, but I think I can mention something that we're doing with one of the clinicians in Jaipur. So we're working on a very very interesting project where we're developing the technology for them, but the use case came from the clinician where they wanted to understand for intraoral wound healing. For those scenarios, they wanted to develop a device that can actually dispense the biomaterial in specific wound areas within the mouth, which is very difficult to heal, and we are helping them out both with the biomaterial as well as the technology. But yeah, I think like you said, more interactions like this, focus group interactions where we discuss specific issues at hand and see how solutions can come both from the tech, biomaterials, or in any form or manner, will actually add value to the entire ecosystem.
Very true.
Yeah.
Dr. Vikas, over to you, sir. Thank you.
Yeah. So thank you, Piyush. In
Thank
fact,
you, Dr. Vikas.
Soft tissue 3D printing is really another great field, additive layering in soft tissues to be used as part of the research, because not much has happened in that field, and with what Dr. Jayesh is already doing at IIT Bombay and with what you have been doing, this will definitely bring a lot of new avenues, it'll open up a lot of new avenues. The only thing is, I'm very surprised that the clinicians, the surgeons across India or across globe, uh, they would not know about what is happening at the ground level from you as researchers. So Dr. Shibu, as he's rightly saying, we all together can play a good role
Yeah.
as far as sensitizing those doctors, who are busy with their clinical practice, but they should know that probably the future is here. That is where the future lies. Like 3D technology is a future. Probably in the present time, again, lot many things are happening in 3D. I'm talking purely in terms of orthopedics and musculoskeletal system. I'm not going into the other domains of medicine. So
Yes.
that is where we want to play a big role. Where I, as an orthopedic surgeon, am surprised in within these 2 days after hearing to lot many research that has been doing by lot many faculties who have presented in the global virtual conference by 3D Graphy. But it is the need of the hour. And so, excellent presentation, Mr. Piyush. Thanks a lot for
Thank you so much, sir.
at
Thank
the
you.
last minute, and thanks a lot, Dr. Jayesh, also for being here at the last minute. So, again, we can open up the panel for some discussion if there are some questions that Mr. Sushant would like to ask, or if Mr. Sudhakar and Mr. Rajesh would like to ask any of the other panelists. Or, on the other hand, if Dr. Jayesh or Mr. Piyush would like to ask to any of us.
Yeah, I think I do have one question in terms of improving. I think on the same lines as what you had mentioned, Dr. Vikas, which was more on the lines of how do we improve, the communication or improve the I don't know awareness about how the technology, what the technology is all about, 3D printing and bioprinting, and there are certain cases where the clinicians might have some ideas, but they just don't have the time to sort those ideas. They will, we understand that clinicians are busy with their patients and the day-to-day running of their centers, all of that. But how can we, as such, companies that are operating in the space of 3D printing or bioprinting, or even researchers who are working in the space, there should be a midpoint where even the clinician knows, okay, if I reach out to this person, probably I can figure out, okay, that can be a solution or something like that. How do we bridge that gap? What would be your suggestion towards that?
So, Mr. Piyush, very valid question. One is the way Mr. Sushant was telling about the consortium that has been created by Dr.
Yeah.
Shibu and all of us, and ultimately what is it that we want is we want continuous communication of the research that is happening, say at your level, Piyush, and that is happening at the level of Dr. Jayesh at IIT, or what is happening and whatever newer products and services that Mr. Sudhakar would want to give to the medical community. And for that, we have to be proactive as to communicate with the regional medical societies. So you
Okay.
could have, so in India has national medical societies, it has state medical societies, and then it has regional medical societies. Now, depending upon the target audience that you think about,
Yeah.
right? Suppose you say that this is the level of target audience we are looking at, and this is the level. I myself, Dr. Shibu, we all together can come and help you out in
Yeah.
doing that process of communication, because Dr. Shibu is himself a media man. He is an excellent communicator, and he can do this job very well. While from the medical side, I can always help him to do the integration. So the connect and the integration can happen. We all can work together as a team, and in coming months and in coming years, we can make the entire communication about the research, about the newer technology, much faster and much easier.
And also now, just to add to this, thanks to you both. See, this is what the consortium is all about. we are here to actually see that what the end user can benefit from. So an expertise like Dr. Jay sir, with a very short time, and I'm really privileged that comes with that kind of a communication that we could immediately respond. And thank you, sir, because of you both sharing these insights, the doctors here could actually get to know that there is so much of things happening. That is only because of the consortium, and this has only happened with time. We build that relationship, that just a call away, without any egos. We are there to showcase and represent it. That's the beauty of a consortium. It becomes very difficult otherwise to get Dr. Jay sir's time. He's a very busy man, but thank you so much, sir. So that is
Shibu,
we have Dr. Narayan Karne also here. We can invite him to
we can invite him
produce
also.
and then talk something on.
He's
also
before he does that, Dr. Vikas, you had asked for a question and a request for help. So I have one. So for example, where we are currently looking for help for nursing homes or hospitals where such orthopedic care is done, where there is an IRB present, right? Because whenever we go for permission, let us say, you mentioned the use of stem cells or use of harvested cells. We need permission from the stem cell committee, National Stem Cell Committee. Now, regulatory processes have become very intricate there. So we need two things. We need a stem cell committee of the hospital where we would like to interact, and we would also need the IRB or Institutional Regulatory Board of that or IEC of that hospital. So we would very much like to be in touch with somebody near us who has both stem cell committee approval and IRB approval, which is not so common. The large government hospitals tend to have it, but then it's difficult to collaborate with them. So we would love to have such interactions with your affiliate members. So with that appeal, I close.
And you are very lucky, because we have Dr. Narayan Karne, who's exactly working on a very similar line. Sir, Dr. Narayan, are you there?
Very timely.
Yeah,
It's
I'm
very
there.
timely that you asked.
And sir, did you hear about the questions that were coming from Dr. Jayesh? Because you must have missed his presentation. He's from IIT Bombay, and he is working on the nanoparticles, and he's working on very high level of 3D printed osteoconductive and osteoinductive biomaterial. And now he has taken it to the level of clinical trials, human trials. He has all the permission, and he wants the support of we as an orthopedic surgeon now to do the required validation and trials for the products that he has. So you have all the legal knowledge, and you have probably the best idea as to what the question that he was asking.
Yeah, that's a great idea. I'm so sorry that I could join only half a minute ago. I was attending another conference. I was coming back from Mumbai to Pune. But it is a really great pleasure, and I really thank Dr. Shibu for doing such a great efforts and working incessantly and with a great determination. And he's taking this innovative technology to a great height, and which should be useful. I really say that is the technology of the future, and which will be useful to all the mankind as well as the surgeons also or healthcare workers. Coming back to the point, as you said, that we can have the clinical trials. Now, here the role of the association comes. Not only at the district level, state level, but even at the national level also we can help you, because this is really an important one. And we can have the multi-centric trial, and we can help you from the association. I can put this in Indian Orthopedic Association. And recently we have based on also Orthopedic Association, of which Dr. Jain is also vice president, and Gujarat, Maharashtra and Goa together. And in that manner also we can conduct all the trials. There are extremely good centers in Maharashtra, Gujarat also for this, and they're willing to do all these things. We need not have to force anybody. And if you go for this multi-centric trial, which is done under the banner of the association, the level of confidence among the hospitals as well as among the patients. So whatever new technology you are bringing, we can go with the help of association and have a lot of number of the patients, which will be helpful for us to prove that even on the international platform also. So I thank everybody, Dr. Shibu, Dr. Jain, and everybody to have such a venture, and we are always with you in all such ventures. Thank you.
So, Dr. Karne,
I would like to have.
Yes, sir.
I have a follow-up on that, if I may. The follow-up is, certainly that's helpful, Dr. Karne. Thank you for that offer. I'll be in touch with you to see how we can involve the association in getting more trial sites. But right now, what we are looking for is, doing some R&D in looking at the role of, stem cells into these scaffolds, and the potential for osteogenic differentiation by virtue of the structure of these scaffolds. So for that, in order to do some stem cell related research, the national regulations now require, that we have approval from a stem cell committee. So we are looking for any nursing home which has a approved stem cell committee IRB, which with whom we can collaborate to check first of all in vitro and then later on in vivo also. For stem. So essentially, stem cell approval committees recognized by the National Stem Cell Committee setup of
I just
the
want to
country.
say that it will be very difficult for the small to medium nursing homes to get the other. Rather, it is time consuming as well as the cumbersome for the small or the medium nursing homes to go for this stem cell approval. Actually, stem cell is being used by many hospitals, doctors on their own on an individual basis at many centers. But now, as you said, that now the recognition at a national level is coming up and we need a approval of such a committee. So there is the role of association will come that if we get that stem cell approval committee at the level of the association, and then from that we can see the individual, I mean, see even there are dedicated hospitals of more than 100 beds in both the states there. So because the doctors and the hospital should concentrate more on the research rather than spending their time on these permissions and other things. So association can help there to get them the permissions. Association can help for bringing all data together, as well as if there is any problem or any issue which they come across, then if it becomes a centralized or the apex body, it helps them that it will be easier for them to do all these administrative procedures and as well as then concentrate on the main subject of the research.
Okay, great. Thank you. So we look forward to your assistance getting some of these stem cell approvals as we go ahead. Thank you, sir.
Thank you. Thank you. Always with Dr. Shibu and all his efforts.
Thank you, sir. Thank you.
Dr. Karne, good evening, sir.
Good
I'm
evening.
Sushant from Orthopaedics. Sushant Banerjee from Orthopaedics. In fact, we are building up a consortium wherein Dr. Jayesh Pilare, Dr. Vikas is there. We can build up a consortium where we can develop a lot of new products which we can easily develop, which
Yeah.
we Indians are capable of developing new products and take it to the global standards. Okay,
Indians are
this is where our interest is
standard.
involved, and we are very thankful to you for helping us in this field.
Yeah. We'll be always there with Dr. Vikas. He's also very enthusiastic and he's an innovative person. I really love to work with him. And Gujarat and Maharashtra can come together and can definitely make changes in this. I mean, positive changes into this. We are always with you, all of you.
Dr. Narayan Karne is also very active with Maharashtra and Indian Orthopaedic Association, Sushanji. So, with all of us together, we will definitely look forward to some newer innings, newer technologies, and Sushanji, working together would be a good initiative now, for sure.
Yeah.
So, I think probably most of the panelists have made their presentations, Dr. Shibu, and we are already touching the time, which is 5 o'clock. Yeah. So this particular track and the topics that we wanted to cover was to sensitize the entire supply chain, right from the manufacturers of the 3D technology machines till the end users, which were the orthopedic surgeons. Right. And I hope a lot of people who must have registered, who are hearing to the different presentations, as well as the lot of interaction that has happened between the entire esteemed faculties which were there very much. They have surprised us as an orthopedic surgeon with a lot of research which they have been doing. All credit goes to 3D Graphy and Dr. Shibu. And on behalf of 3D Graphy, on behalf of Dr. Shibu, on behalf of Indian Orthopaedic Association, the orthopedic doctors across India, I would like to thank the entire esteemed panel who have spared all that precious time, and you have shared your research, you have shared your knowledge, and you have enabled we as an orthopedic surgeon also to understand that so much of work that is going on, to start with, the implants which we can make from the additive layering, to the soft tissues, which Mr. Piyush was saying, to the scaffolds, which are biomaterials, which are osteoinductive, osteoconductive, and altogether already a possibility of doing all the human trials. So this is very exciting. So going ahead with all that, this particular session was focused for orthopedic surgeons, and I hope all the orthopedic surgeons who have come as delegates also must have got a fair idea about the medical future as well as the orthopedic futurism, as I would label. So thank you lot, Dr. Shibu, and thank you all the panelists.
Thank you so much, Dr. Vikasji. And also, now that this content will also be proliferating this through our 3D Graphy news, because that's our conscious efforts. Because now, beyond events, now we are also 3D Graphy is also been responsible to actually take this to the next course of action in terms of communicating it to the larger audience. So we will also be creating a link, sir, and we'll also be sending it to you. And maybe you can help us to share this with all the IOA members, and also
Yes,
Narayan sir is also here, and various other associations. I mean, within the smaller bodies also, wherein we can send it, so they also get to know about this particular content of this particular platform. Apart from that, gentlemen, doctors, and senior respondents and technology experts, 3D Graphy News is also a two-way communication that we've actually been able to build. It's based on an AI automated platform, which will also have, which will also be automatically. This will also, track information, and also will be connecting cords with, getting it activated in terms of SEO, search engine optimization. So we are building that, and it's slowly taking up a good lead for 3D technologies in the country, and globally also we are trying to build on this. So 3D Graphy News is a platform. So where we will be also trying to get the maximum information source, because there is never a dearth of content, but this content needs to actually be shared so that everybody is well equipped with knowledge and information about this technology. And what we are also doing is 3D Graphy News Spotlight is a new initiative, which I was just sharing, that we will need to do these series of initiatives, because it's important that everybody gets to know about this. I was just talking to Dr. Pramod, Dr. Vikasji. He is an oncosurgeon. He was supposed to do, he's to join in the next session. So I'm saying some beautiful technology, share of content was shared in this session, but probably he would have missed out. So where I'm coming from is I'm always in the quest of seeing that everybody gets to know about these information. So what best we can do is to have a series of initiatives wherever people can join, whenever they can join, they can take the best out of it. So that's something that we are also initiating, which is called 3D Graphy News Spotlight. So every day we can have one initiative for an hour or a half, depending on people's time and availability in terms of propagating this technology to an audience that we would want to reach out to. Thank you so much, gentlemen, and we will now move to the next session. So while you actually, come out of the session, you can just log into the next session, and some of them who are speakers here can also be audience there, and also be updated of what is new in terms of experts going to be sharing on 3D printing and high precision sarcoma surgery. So there are oncologists who will be sharing their presentation, and also some materials, antimicrobial materials will also be discussed, and also on simulation software, which is to be also discussed, because dissection and also trying to also see how simulation can really help in terms of making the course better through the technology is also very, very important, because we spoke about 3D printing to a large extent, but software and simulation is also equally important. So thank you, gentlemen, and we will connect on in the next session. Thank you.
Thank you. So we can all leave, Shibu, with your permission, all of us.
Yes, sir. Please.
Okay.
Thank you so much.
Thank you so much. Thank you, everyone, and have a nice day. Thank you.
You too.
Thank you.